Swayam Prabha. Digital India. Educated India.
In the last class we have seen technical comparison of the various hydrogen production route. In this class we will see the economics associated with the different hydrogen production methods and what is the global and Indian status. So, this is the last class on the hydrogen production, and thereafter we will, in the next class we will start with the hydrogen storage methods. Before we go on to the economics, we will quickly revise some of the definitions or terms which we use in energy economics. The foremost term that we use in energy economics is simple payback period. So, this is the number of years in which an investment pays itself. However, this term, it does not use the time value of money or the life of any plant. So, in order to include that, there are other terms which are used like the net present value or life cycle cost. When it is net present value, it takes into account the savings and the cost. So, savings minus cost, and then in the denominator is the discount rate. Discount rate considers the time value of money. So, when some investment is done today, what is the expected gain or what will be the worth of that money which is invested in future. So, that is considered by the discount rate, and this is summed over the number of years. So, for a kth year, this is Bk, the benefits minus the cost Ck in the kth year over 1 plus d to the power k. D is discount rate, k is the year. Now, when we have to find the life cycle cost of a plant, of an energy plant, energy producing plant, then that can be obtained by adding the initial investment and the present value of all the expenses summed up over its lifetime. So, this is the present value of all the expenses during its lifetime. To that we have added the initial investment. Now, if this expenses remain constant over years, for this uniform C, we can write the life cycle cost by the initial investment plus expenses over capital recovery factor, that depends upon both the discount rate and the years. Now, the annual cost associated with owing as well as operating an equipment can be obtained as annual life cycle cost, which is the initial investment times the capital recovery factor plus the annual fuel associated operation and maintenance cost, non-fuel operation and maintenance cost. So, this is how we can get the annual life cycle cost of a energy plant, energy producing plant. We can find out also the levelized cost of energy by dividing the annual life cycle cost by the amount of energy that plant is going to produce over its lifetime. So, the life cycle levelized cost of energy is given by annual life cycle cost, which we have seen is the initial investment times the capital recovery factor and the expenses associated with the fuel related and non-fuel related operation and maintenance, divided by the total energy being produced during the life cycle of the plant. So, that gives the levelized cost of energy. On the same pattern, we can also calculate the levelized cost of hydrogen, and that levelized cost of hydrogen is the discount rate levelized cost of hydrogen is the discounted lifetime cost of building and operating a production system, and it is expressed as the total cost of the plant divided by the total amount of hydrogen which is being produced over the lifetime of the plant. So, the total cost divided by the total amount of hydrogen that is expected to be produced by that plant over its entire lifetime, and this is only the production cost is included while calculating the levelized cost of hydrogen, not the storage or the transport or the end use cost. We can also find levelized cost of hydrogen as net present value of the total costs, which includes both capex and opex. So, it is the net present value of the total cost summed over the number of years for which the plant is operational from commissioning to decommissioning divided by 1 plus discount rate to the power n. And similarly, we can find out the net present value of the hydrogen being produced, and the ratio of the two net present value of the total cost to the net present value of the hydrogen production will give us the levelized cost of hydrogen. So, these are some of the terms we should know before we look at the cost analysis of the hydrogen which is being produced through different production routes. Now, if we look at the current global status, in the year 2020, 90 million tons of hydrogen was produced globally. Out of that 90 million tons, 79% of it, 72 million tons was produced in dedicated hydrogen production plant. Another 21%, which is 18 million ton, was produced as a byproduct hydrogen in refineries, primarily in refineries. Now, this 90 million tons, out of that 72 million tons was used as pure hydrogen in ammonia synthesis and in the refineries. Another 18 million tons used as mixed gas with other gases, basically for methanol production or for DRI for steel production. Now, in the various production routes, natural gas is the dominant fuel which is used for producing hydrogen, and steam methane reforming is the dominant process for producing hydrogen. So, about 59% of the production of hydrogen was using natural gas, and approximately 240 billion cubic meters of natural gas was used for producing hydrogen, which is approximately 6% of the global natural gas consumption. 19% of hydrogen produced using coal, and about 115 million tons of coal equivalent is used for producing hydrogen, which is 2% of the global coal demand. 21% obtained as byproduct, 0.6% produced using oil, and the remaining using low carbon technology, which includes electrolysis, which includes fossil fuel plants which have carbon capture, use and sequestration. Now, out of this 90 million tons, we have seen most of it is being produced from fossil fuels and without CCUS, and because of that there are 900 million tons of carbon dioxide emissions which are related to the hydrogen production, which corresponds to 2.5% of the global carbon dioxide emissions in the energy and industry. Now, there are various technologies which exist for low carbon hydrogen production, like production from water using either thermochemical cycles or from electrolysis, or it can be produced from fossil fuel plants with CCUS or from biomass gasification. But the current status is only 30 kilotons of hydrogen is being produced from water electrolysis, and there are about 16 fossil fuel plants which have carbon capture, use and sequestration, producing 0.7 million tons of hydrogen in these plants. However, it is expected that the scenario may change, and in the net zero scenario, the production of hydrogen from the current 90 million tons will increase to 200 million tons by 2030. And it is projected that out of that 200 million tons, 70% should come from electrolysis and fossil fuel with carbon capture, use and sequestration. Remaining will come from plants which are not integrated with CCUS. By 2050 this number will grow to 500 million tons, and all this 500 million ton is expected to come from low carbon technologies. Now if this is the forecast, for providing that much amount of hydrogen as we move in the net zero scenario, the requirement of electrolyzer capacity, which is currently 0.3 gigawatt installed capacity, will grow to 850 gigawatt by 2030, and it will be 3600 gigawatt by 2050. So this is the requirement in terms of the electrolyzer capacity. At the same time, when it is net zero scenario, the fossil fuel plants needs to be integrated with CCUS. So carbon dioxide capture will be required. Currently the status is 135 million tons of CO2 is abated with using CCUS at the production plant site, which will grow in 2030 to 680 million tons, and in 2050 it should grow to 1.8 gigatons or 1800 million tons of carbon dioxide per year. When these renewable methods or water electrolysis or plants integrated with CCUS, these all will be used for hydrogen production, or in the net zero scenario, the water that will be required for these technologies will also grow. Now currently if we see, if the hydrogen is being produced from electrolysis, roughly we require 9 kg of water per kg of hydrogen being produced. When it is steam methane reforming integrated with CCUS, there is a requirement of 13 to 18 kg of water per kg of hydrogen being produced. In coal gasification, depending upon the mining method, it varies from 40 to 85 kg of steam requirement per kg of hydrogen. However, this requirement will be in net zero scenario of 5800 million cubic meters of water, which is 12% of the water being consumed in the energy sector. It is also possible to use sea water, because most of the places which are water deficient may not be able to supply or meet this much requirement of water. So in that case, sea water can be used through reverse osmosis desalination method, which will require 3 to 4 kilowatt hour per normal meter cube of water, and that could add an expense of 0.7 to 2.5 dollar per normal meter cube, and there will be a marginal increase in the cost of hydrogen being produced. So in that case, the cost of hydrogen will increase by 0.01 or 0.02 dollars per kg of hydrogen. Now if we look at the plants which are coming up, the plants which are being already under construction or at later stage of planning for commercialization development, then roughly about 350 such projects of electrolysis are there, which could account for 5 million tons of hydrogen being produced through electrolytic route. There are currently 16 fossil fuel based plant with CCUS, and total that will account for 56 such projects where the production of hydrogen from fossil fuels integrated with CCUS will account for 9 million tons of hydrogen being produced by 2030. Now if we also include 40 more projects which are currently globally at an early stage of development, then the electrolytic hydrogen production capacity can increase from 5 million tons to 8 million tons by 2030. By 2050, as per the pledges, the strategies, the roadmaps which various countries globally are coming up, the different announcements that they are making, the pledges which are coming up in the clean hydrogen production scenario. By 2050 it is expected that 250 million tons of hydrogen will be produced, and out of that 250 million tons 51% will come from electrolysis and 15% will come from fossil fuels plants which are integrated with CCUS. The rest is going to come from plants which are not integrated with carbon capture, use and sequestration. Now if this is the scenario, then this 51% of hydrogen which is coming from electrolysis will account for increasing the electrolyzer capacity to 1350 gigawatt, and the carbon capture that needs to be integrated with the fossil fuels has to increase to 0.4 gigatons of carbon dioxide capture per year. When it comes to cost analysis, we know that the fuel which is used widely we have seen is natural gas for hydrogen production, and the method is steam methane reforming. This is the most cost effective method. So, the levelized cost of hydrogen which is produced using steam methane reforming, it lies in the range of $0.5 to $1.7 per kg. Now, there is a huge variation in the cost. The reason is the regional variation in the cost of the feedstock, natural gas. However, this is without any carbon capture, use and sequestration. If it is integrated, the plant is integrated with CCUS, then there is an additional increment in the cost of hydrogen produced, levelized cost of hydrogen produced by $0.5 per kg of hydrogen, and this is higher than the without the CCUS. But this price is still much lower than the cost of hydrogen which can be produced from renewables. So, if it is produced from renewables, the cost lies in the range of $3 to $8 per kg of hydrogen being produced. And in this cost range, the major component is of the electricity which is being used for electrolysis. So, the renewable power, its cost accounts for 50 to 90% of the total cost of hydrogen being produced. And that depends on both what is the electricity price at which we are getting that power and the full load hours of electricity supply, for how long we can use that surplus electricity for producing hydrogen, or for how many hours is the electrolyzer running on the supply of that electricity. Now, there is a requirement of reducing this cost from $3 to $8 so that it can become compatible or comparable with the fossil fuel based hydrogen production. This cost reduction can come only when the price of the renewable power or the cost of electrolyzer comes down, and it is expected that with economies of scale, with more deployment of renewable, the renewable cost, the renewable power cost will come down. And this gap between the cost of hydrogen being produced from reforming and from renewables will decrease with the reduction in the cost of renewable power as well as the decrease in the cost of electrolyzer, the capex cost of the electrolyzer. There is another way in which we can see that the cost gap between the two methods will reduce, which will be when the carbon dioxide emissions are priced. So, price associated with the carbon dioxide emissions will also reduce this gap between the fossil fuel based production and renewable based production. For example, if $100 per ton of carbon dioxide cost is added for the carbon dioxide released in the environment, then the cost of production from natural gas will increase by $0.9 per kg. So, this is one more method by which the gap between the two prices can be reduced or shrinked. Now, when it comes to production from steam methane reforming and carbon capture, use and sequestration, the price typically lies in the range of $1 to $2 per kg. So, important is to produce hydrogen in a sustainable manner from renewables. For that, the cost of renewable electricity should come down, and that will be crucial towards reducing the price of hydrogen from electrolysis. And there has been several initiatives globally to bring down that cost, like one of the initiative is US Hydrogen Earthshot initiative, wherein they are considering to bring down that cost by 2030 to $1 per kg of hydrogen being produced. And it is expected that the cost of renewable electricity, when it is considered like $20 per megawatt hour, then it can come down to $1 per kg of hydrogen being produced. That was $20 per megawatt hour was without including capex and opex. Now if it has to further come down, if that also needs to be included. Now this price of renewable electricity can come down at places where there is more of deployment, where there are more number of sunshine hours, like Middle East, like in country like India, where we have ample amount of renewable source which is available, we have ample sunshine hours, solar insolation available. Similar to that, a project, a utility scale solar PV project, that tendering has been done in Middle East, and the bid that has been done in 2019-2020 has even shown prices as low as $14 to $17 per megawatt hour of the electricity price, renewable based electricity price. So, all these will be crucial towards bringing down the cost of renewable electricity. At the same time, requirement is that there should be improvement in the efficiency of electrolyzer and the other balance of plant. So, it is expected that in long run the scenario will change. There will be reduction in the renewable price, there will be economies of scale, bringing down the cost of electrolyzer, and we will have a learning experience with these scaling up that will further lead to better understanding. But currently there is lot of uncertainty associated with how the price and the deployment will take place in future. If we look at the current electrolysis status, around 0.03% of the global hydrogen is being produced using water electrolysis. So, out of the 290 megawatt which was produced using water electrolysis in 2020, 40% of it was in Europe. The installed capacity of 290 megawatt global, out of that 40% in Europe, 9% in Canada, and 8% installations were in China. And out of this 290 megawatt, if we see the different technologies which we have already studied in this course, alkaline water electrolysis accounted for 61% of the total hydrogen production using the electrolytic route. PEM electrolyzer 31%, and rest are either unspecified or SOEC, solid oxide electrolytic units. The cost of alkaline water electrolysis lies in the range of $1000 to $1400 per kilowatt hour. For PEM it is around $1750 per kilowatt hour. It is expected that by 2030 this capacity will increase, considering whatever plants which are under construction or projects which are planned, this capacity will grow to 54 gigawatts. Now if we also consider all the projects which are in their early stage of drafting or development, then this capacity can even grow to 91 gigawatt by 2030. So the two major contributors will be in Europe about 22 gigawatt, Australia 21 gigawatt, Latin America 5 gigawatt, and Middle East 3 gigawatt, and remaining from the rest of the world. It has also been seen that the average plant size over a period of time will increase. So currently if we see, the average plant size of an electrolyzer lies is roughly about 0.6 megawatt in 2020, but now there are projects which are coming up which have plant size of 100 megawatt. There are plants which are even planned which will have capacity of 1 gigawatt, like a plant in Australia which is under the green energy hub. It has 50 gigawatts of solar PV and wind installation that will be used for hydrogen production, and that will have a capability of producing 3.5 million tons of hydrogen per year. So, what is expected is that there will be economies of scale as the deployment will increase. We will have a better learning that will further lead to cost reduction from current, which is say $1000 to $1750 per kilowatt. But there are certain installations in China where they have reported this cost range to be something between from $750 to $1300 per kilowatt. Even there are reports wherein they say the cost can be, the capex can be as low as $500 per kilowatt, and all these will make a difference in terms of the electrolysis price. Now, out of the major manufacturing which is going on globally, the largest manufacturer being Europe with 60% of the manufacturing capacity, China being the second with 35% manufacturing capacity, and now there are several major companies which are entering into expanding towards their manufacturing capacity of electrolyzers, like the Thyssen Group, IITM, Cummins, Nel, Hydrogen Nel. So, there are several other companies which are expanding, but then when the capacity of manufacturing will increase, the requirement of materials will also increase. But we expect that in future with more technological advancement, the materials which will be used will be, the amount of material, precious materials that will be used will also reduce. Now, the major factors which contribute towards the total cost includes the electricity cost, which is the major component, 50 to 90% of the levelized cost of hydrogen, the capital expenses, conversion efficiency, and the annual operating cost. We know that with the grid electricity, considering that the electricity price being $50 to $100 per megawatt hour, this may not be this may not reduce the cost of hydrogen, and the cost of hydrogen will be roughly lying between $3 to $5 per kg of hydrogen being produced, considering the capacity factor of 90% and capex as low as say $500 per kilowatt. So, the cost will reduce if it is being produced from renewables, and let us say if it is being produced at a zero cost and considering an operating hour of 750 hours per year, still the cost will be $3 per kg. So, it is expected that with using the renewable power, say solar or wind power, the cost should further go down as the economies of scale work well. Now, at places where there is larger sunshine hours, there is high solar insolation available, like Middle East, like country like India, the cost will go down in the zero emission scenario. Now, considering the current status say 2020, where the cost of renewable electricity is like in Middle East, it is taken as $20 per megawatt hour. The cost is $3 per kg of hydrogen being produced with a capacity factor of the plant 32%, considering a capex of electrolyzer being $1000 per kilowatt. Now, it is expected that in 2030 the cost of renewable price, electricity price, if it reduces to $70 per megawatt hour, the cost of hydrogen will go down to $1.5 per kg. Considering capex also will come down to $320 per kilowatt, and then it will become equivalent to the hydrogen which is being produced from natural gas integrated with CCUS. Further price down of the renewable electricity to $12 per megawatt hour will bring down the cost of hydrogen being produced to $1 per kg, and then it will become equivalent to natural gas based hydrogen production without CCUS. In Europe, the hydrogen production could be from offshore wind, and then from there it could be taken through pipelines, and that will reduce the cost of transmission and distribution, which could be the losses associated with that. Considering that if the current prices associated with the wind power, the cost of renewable electricity currently are higher, $60 per megawatt hour, and that is responsible for $4.5 per kg, a higher cost of hydrogen being produced, considering a capacity factor of 50%. But it is expected that by 2030 the cost of renewable electricity from wind will come down to $30 per megawatt hour, and then the hydrogen production cost will be $2 per kg, considering the capacity factor of 57%, considering wind turbines which are larger in size, and then in 2050 this price, renewable electricity price, may go down to $25 per megawatt hour, resulting into the cost of hydrogen being produced to $1.5 per kg of hydrogen, considering a capacity factor of 60%. So, this is how the scenario will change. Now, we know that the other possibility could be for a sustainable hydrogen production, that we can produce from the fossil fuels and then integrate CCUS along with it. So, steam methane reforming and coal gasification, we know that these are very well known technology, but then they are the major polluters also, which will release carbon dioxide emissions during the process of hydrogen production. So, it is essential that CCUS should be integrated. It is not only to reduce the emissions associated with the hydrogen production, but at the same time when CCUS is integrated, we can still use these low cost technologies, we can scale them up and meet the growing demand of hydrogen. When CCUS is being integrated, then the cost of hydrogen being produced increases roughly about $0.5 per kg of hydrogen. With steam methane reforming, if we consider the emissions, then it is 9 kg of carbon dioxide is released per kg of hydrogen being produced. We have seen in detail that the emissions are taking place on both the end, when it is used as fuel, burning in the burners and providing the reaction heat. So, 30 to 40% of these emissions occur when it is being used as fuel. Rest of the emission 60 to 70% comes when it is used as feedstock. So, in the product gas stream, that is more concentrated. So, if we capture both at the fuel end as well as at the product side, 90% of that capture is possible, and for that the cost will be $50 to $70 per ton of carbon dioxide being captured. Another method which we have seen was autothermal reforming. We can achieve higher capture rate because in autothermal reformer the entire carbon dioxide which is being produced is concentrated, and the same reactor the fuel is burnt and the product stream is obtained. So, we can get concentrated carbon dioxide. So, if we capture that, so we can increase that capture rate from 90% to 95%, or we can have the same capture rate but at a relatively lower cost. In case of coal gasification, the amount of carbon dioxide emission is 20 kg of carbon dioxide per kg of hydrogen being produced. Now, the current situation is there are 16 projects with carbon capture, use and sequestration integrated with the fossil fuel production plants, producing 0.7 million tons of hydrogen and abating 10 million tons of carbon dioxide which is produced in the process. Now, if we consider that there will be a carbon dioxide price penalty that will be levied in the future on the uncaptured carbon dioxide, and that will be about say 5 to 10%, then the production cost with CCUS will slightly increase. Now, these 16 projects are existing. There are 40 more projects under development. These are 35 integrated with natural gas based production, 4 with coal, 1 with oil. It is expected that by 2030 when fossil fuel plants, these plants will be operational with CCUS, then we will be able to produce 9 million tons of hydrogen from these plants where carbon capture will be done, considered. Now there are certain future technologies which are not at commercial scale, at a higher TRL level, like solid oxide electrolysis, which we have seen. This is the high temperature electrolysis or steam electrolysis. Currently this is at a TRL level of 6 to 7. This is for producing synthetic fuels, like it is used with renewable power and of capacity 720 kilowatt, wherein even the waste heat is used for producing hydrogen for DRI in steel production. There is one more plant which is coming up of capacity 2.6 megawatt in Rotterdam. Methane pyrolysis is another technique which is a future technology having a TRL level of 3 to 6. So there are plants like Monolith Materials in US, they are using thermal plasma for the cracking of methane. There was a pilot plant in Nebraska and now they are planning for an industrial scale plant. There are several plants which are coming up in Australia, Germany and Russia, US. So the technology will grow in future. Anion exchange membrane based electrolysis, which is at TRL level 4 to 5, and then kilowatt scale electrolyzers are being developed by Napter Germany. It can be also electrified steam methane reforming, which is at TRL level 4. Helder Topsy, they are using this technology, but the demo that it is still at a lab scale using the low carbon electricity, steam methane reforming is being performed. Now if we quickly look at the cost of hydrogen production from the different routes which we have seen in this course, the cost of hydrogen production from SMR we have already seen 0.7 to 1.5 dollars per kg without CCS. If it is with CCS, 1 to 2 dollars per kg. Partial oxidation 1.35 dollars per kg. Autothermal reforming 1.3 dollars per kg without CCS. With CCS 1.48 dollars per kg. If it is coal gasification 1.34 dollars per kg without CCS, and that increases to 1.63 dollars per kg with CCS. Methane decomposition still it has not been commercialized. With biomass pyrolysis the cost lies in the range of 1.59 to 1.7 dollars per kg. With biomass gasification 1.77 to 2.05 dollar per kg. Dark fermentation 2.57 to 6.9 dollars per kg. Photo fermentation 2.83 dollars per kg. Thermochemical cycles based on whether the energy required for high temperature cycle for providing the heat for the high temperature cycle is by means of nuclear, then it is 2.17 to 2.63 dollars per kg. If it is from solar 7.98 to 8.4 dollars per kg, and the different cycle costs. When electrolysis is from grid electricity, then 5.73 to 8.54 dollars per kg. From PV 5.78 to 23.27 dollars per kg. From wind 5.27 to 9.37 dollars per kg. Photolysis 8 to 10 dollars per kg. Biophotolysis 1.95 dollars per kg. So these are roughly the costs of hydrogen production through all the routes which we have studied in this course. Now I will quickly look at the Indian context. In India 6 million tons of hydrogen is being produced annually, 3.2 million tons for ammonia production, 2.6 million tons for refineries, 0.2 million ton is obtained as a byproduct hydrogen from chloralkali plant. So if we see the levelized cost of hydrogen, from electrolysis this cost is higher, 400 rupees per kg of hydrogen being produced. From natural gas this lies in the range of 140 to 160 rupees per kg of hydrogen. This variation is because of the varying natural gas prices. and it is expected that by 2030 this will be 150 rupees per kg of hydrogen, by 2050 it will be 80 rupees per kg of hydrogen. Using coal gasification, the price is in between 150 to 300 rupees per kg without CCUS. However, if we integrate CCUS, then the price goes up to 240 to 400 rupees per kg. Coal gasification is promising in the Indian context because we have huge reserves of coal, but the problem is we have a high ash coal. So, either the technology should be developed so as to use the Indian coal, or then we will depend on the imports for low ash coal. From biomass, the price is 200 rupees per kg of hydrogen being produced. Now, to summarize this part, we have seen that hydrogen production from fossil fuel is the most cost effective route for hydrogen production, economical, but then it is not a sustainable method. For sustainable hydrogen production, it should be from either come from the energy which is required for producing hydrogen should come from renewables, or it should be produced from fossil fuel with CCUS. Now, there are several advancements going on globally. There are different countries which are coming up with their road maps, their strategy documents, they are pledging towards reducing the emissions, and it is expected that the scenario will change in future. Thank you.